Alright, so in this video we're going to finish the proof of the power series theorem, finally. We're working right now on parts 4 and 5, which talk about the fact that a function defined by a power series is analytic in the interior of the circle of convergence. And then part 5 just says that you can differentiate that function by differentiating the series term by term. All right, so we need a lemma. This part, step B, just basically consists of a lemma, which deals with a situation where essentially you have a sequence of functions converging to a function, and you have the derivatives of those converging to some function in a different sense. These are really two different kinds of convergence. This one is pointwise convergence. I'll explain the meaning of this in a moment. This other convergence has to be a little bit stronger type of convergence called uniform convergence. But then the conclusion is that basically f is a differentiable function and its derivative is g. All right, so that's essentially what the lemma says in a nutshell. But let's look more carefully at the details, and then also the proof. All right, so we're going to be working on a compact non-empty set, capital K, some subset of the complex plane. And we'll use this notation if we take a function f defined at least on K. So here f has to have the property that K is inside its domain. Okay, the domain of that function doesn't have to be exactly K, but the domain has to include K within it. And then it makes sense then to say that if we allow z to take on every value in K, take on every point in K as a value, you can plug those into that function f and take the modulus. Right? The modulus is a non-negative expression, and then you can take the supremum of those non-negative numbers. Right? Now, usually we write this as maximum, the maximum modulus. But you see, I'm not assuming f is continuous. This expression here makes sense even if f is a discontinuous function. If f happens to be continuous on K, then the modulus of f will also be continuous on K, because the modulus is certainly a continuous function. And then the extreme value theorem applies. The extreme value theorem will tell us that in that case, the modulus of f of z acquires a maximum. It actually takes on a maximum value because K is compact. Right? But we don't know that f is continuous. This concept is perfectly well defined even if f is not continuous. You can still take the supremum. Okay? And the supremum will be greater than or equal to 0 because all the numbers that you're taking the supremum of are greater than or equal to 0, right? Because they're moduli. Anyway, so the answer is going to come out to be in this interval, but it might take the value plus infinity, because these numbers here may be unbounded as z moves around K. And because f could be discontinuous, it may be that there's like a sequence of points in K for which the values f of those points just get infinitely large in modulus. And in that case, the supremum would be plus infinity. So we have to include plus infinity. That's why I have a square bracket here rather than a round parenthesis, because plus infinity is being included as a possible value. All right, but that expression, that supremum, we're going to denote this way. And we call this the sup norm of the function f on K, or we can also call it for short the K norm of f. Okay, so either expression can be used. All right, so what does that represent? It's basically, we use the supremum when the maximum is not available, because the maximum may simply not exist. Like, there may not be a maximum. You see, even if it's bounded, right? Even if these values here are bounded, they still may not take on a maximum. They may just approach arbitrarily closely to a supremum. So when the maximum doesn't necessarily exist, the supremum is kind of the next best thing. It's a substitute for the maximum in cases when there may be no exact maximum. But the rough idea is that we're just taking the maximum modulus that that function achieves on the set K. Taking the modulus of f of z, and then just letting z run through that whole entire set K, taking on every point in K as a value, and then you collect together the modulus of f for every such point z, and then maximize that. But we have to supremize instead of maximizing, just for technical reasons. And so that is a kind of norm. It's a measure of how big the function is, at least on K. It's relative to K. If you change the region K, change that compact set to some other compact set, then for the same function, f, we would of course expect the norm to change as well, because it's relative to that set. It sort of measures how big that function is on that set by maximizing the modulus that f takes on, but just on that set. So for example, if I have a compact set K and then a somewhat smaller compact set L inside K, you see that the function may have a very small modulus throughout here, but then the modulus of the function may get very large, let's say over here. So the norm of the same exact function will be different if you consider the K norm versus the L norm. All right, so we're going to use that concept. But now here's the beginning of the actual statement of the lemma. That was just a little introduction of this notation or concept of the K norm, which will be used in this theorem. Okay, the actual statement of the theorem goes like this. Suppose we're given a sequence of functions, f sub n, so n takes on the values 0, 1, 2, etc. So it's an infinite sequence of functions, and every one of them is analytic on K. And I'll remind you that that's actually just a shorthand for something. Being analytic on K really means being analytic on some region that contains K. Because K itself is not a region. K is compact, so it's a closed set. A region is an open, connected set. But when we say that a function is analytic on something that's not a region, what we mean is that the function is actually analytic on some region that contains that set. Right? So for example, f0 will have some region, will be analytic on a region u0 with K inside it. Right? Then also f1 will be analytic on some region u1 where K is inside of u1 as well. Right? And similarly, f2 is going to be analytic on some region u2, and K is going to be inside u2. Right? So notice that these regions don't have to all be the same. f0 and f1 and f2 could all be analytic on slightly different regions, as long as all of those regions contain this compact set K. All right, so that's one assumption about our sequence of functions. All of them are analytic on K. Now, let's also notice that this also implies that the first derivatives of those functions are also analytic on K. Right, let me just explain why briefly. I'll give myself a bit of room here. In fact, yeah. All right, so we know that f sub n is analytic on this region u sub n, which contains K, capital K. That just means that fn prime exists on u sub n. But then in complex analysis, that actually tells us that fn prime is continuous. And we need that fact. We're going to need that fact later in the proof. Fn prime is continuous, actually, on this entire region, and hence on K, because K is inside of u sub n. So the point is that we can infer that the derivatives are continuous. How is that? Well, in complex analysis, in fact, we know that every analytic function is infinitely differentiable. If you have an analytic function on a region, this is a region, u sub n, and this is an analytic function on that region. Okay, so if you have that situation, then we know that the function f sub n will be actually infinitely differentiable on that region u sub n. Okay? And that means that the first derivative is also infinitely differentiable. So the first derivative is itself a differentiable function, and therefore is itself a continuous function. And that's really the key. We need these derivatives to be continuous, just for technical reasons, okay, on those regions, and therefore they're all continuous on K itself, since K is inside a region on which it is continuous. All right, now, in real calculus, this does not follow. You see, in real calculus, the function fn could be differentiable. Let's say f sub n is just an ordinary calculus function, a real valued function of a real variable. Well, we could say, okay, let's suppose it's differentiable on u sub n, which is an open subset of the reals. And k is some compact subset of the reals that's inside of u sub n. Right? Well, that will certainly tell us that fn prime exists on this open set. Right? So u sub n is some open connected set, or in other words, a region, but in one dimension. Anyway, so yeah, differentiable means that the derivative exists, but it does not imply that the derivative is continuous. We can't infer from the existence of the derivative that the derivative is continuous on that same region. So in the real analysis version of this lemma, you just have to add the continuity of fn prime as a hypothesis. See, in the complex version, we don't have to state that hypothesis because it follows from general facts about analytic functions. Basically the fact that when a function is once differentiable on a region, it's actually infinitely differentiable. But that's very special to complex analysis. It doesn't hold in real analysis. So this lemma that we're stating here has also a real calculus version. And the proof is virtually identical. But you need one extra hypothesis in the real version. And that is that the fn primes should also be assumed continuous on K. Right? So just take note of that, because the proof I'm going to show you here is valid both in complex analysis and in real analysis. You get the same exact theorem, and then you can use it in the same way to prove the power series theorem, like parts 4 and 5. So essentially all the math we're doing right now on the power series theorem is applicable equally well for power series in a complex variable with complex coefficients, or a power series in a real variable with real coefficients. It's the same exact theory, which is why I'm taking the approach that I'm taking, even though it's longer. See, the approach Alfors takes in his book, which, by the way, is very elegant, and I encourage you to read it. You all have a PDF copy that I posted, and you can download that to your own machine, just so that you don't have to scroll all the way down to the bottom of the classroom page every time. Anyway, go and take a look at that PDF. You can look in the table of contents, just look for power series. And you'll read in the space of just a few pages, Alfors is able to give the kind of skeleton of all these arguments, and it's very elegant, very beautiful. But you see, his argument uses the Cauchy integral formula in an essential way. So it means that it's only applicable in the complex case. It doesn't help you prove the similar theorem in the real case. Well, I think that the theorem in the real case is also extremely important. So that's why I prefer this method, which applies with some very tiny modifications. It applies to both types of analysis. Okay, so but in the real case, you just have to take note of the fact that the continuity of fn prime on K, this statement here, this statement right here, is not something that you get for free in the real case. You have to take it as an extra hypothesis, take it as an extra assumption. But we do get it for free in the complex case. Okay? All right, next, we're going to have these two functions, f and g, also defined on K. And the role of those two functions is to serve as a limit, like f is going to serve as a limit of this sequence of functions, and then g is going to serve as a kind of limit of the derivative sequence. But the two limit processes are a little bit different from each other. Okay, you'll see that when I list all the assumptions here. So let's actually jump right down to that right now. Okay, the fn's are converging to their limit function f in a pointwise fashion. That's what PW stands for, pointwise. And then this on K. The other type of convergence that occurs here is like the sequence of derivatives, fn prime, is going to be converging to its limit function, g, in a different way. This U is short for uniform convergence. Okay? Also on K. Two different types of convergence when we're dealing with sequences of functions. Notice these are not sequences of numbers. These are sequences of functions that are converging to functions. So yeah, with numbers, when you have a sequence of numbers, and then the limit is also a number, there's only one type of convergence. It just means that the distance between the sequence and its limit gets arbitrarily small and stays arbitrarily small from some point on. Okay, but when you have a sequence of functions, all on a common domain, all on a common set, in this case K, right, and then there's a limit function. There are different modes of convergence, different types of convergence, and these are two of them. Okay, well, let me explain what each of them means. Right, piecewise is pointwise is very easy to understand. All it means is that when you pick any z in the set K and plug that into both the sequence of functions and the limit function, see, that gives you a sequence of numbers. See, because once you plug in a specific point, then you're just getting a number. It's no longer a function. If I write fn, that's a function. But if I write fn of z, that's a number. Okay, and then this also is a number, f of z. And then this is just the ordinary sense in which a sequence of numbers can approach a number. But it has to hold for each z in K. Right? Now, you see what that means is that at each individual point z, you have this convergence happening. Fn of z is approaching f of z. But if I move to a different point in the same region, the convergence may happen a lot more slowly. So I might get a very rapid type of convergence at one point in K, and then if I move to another point in K, I may get, a glacially slow convergence. The rates at which these convergences are happening are unrelated from one point to the other within that set K. So it's pointwise because at each separate point you have a convergence, but there's no relationship between the rates of convergence at different points. And so that's a fairly weak manner in which functions can converge to a limit function. But that's all we require, at least for the fn's. They have to have a limit function, but they can approach their limit function in this rather weak way, pointwise, on K. All right. Now, the other sequence of functions that we're working with is fn prime, right, as n takes on these values. And that is also assumed to have a limit function, g. But that type of convergence it can't be pointwise. That's just too weak of a type of convergence to make this theorem work. To make the theorem actually work, technically, we need this convergence to be of this stronger type called uniform convergence. Okay, uniform convergence on the set K. Now here's what that means. It means that if we take the K norm of the difference between the two, that approaches 0 as n goes to infinity. And so as n increments upward, 0, 1, 2, 3, 4, this difference, fn prime minus its limit function, will have a smaller and smaller K norm. And those K norms not only get smaller, like as an overall trend, but they get arbitrarily small. And they stay arbitrarily small from some point on in the sequence. All right? So what does the K norm of that difference represent? Well, it's a kind of distance between those two functions with respect to the set K. Remember that the k-norm measures how big the function is on that set. It's basically the maximum modulus that the function achieves on that set. Although technically it's not necessarily a maximum. It's the next best thing, which is a supremum. But it's actually very profitable to think of it as a maximum modulus because it's easy to understand it in that language. Okay, so yeah, technically it may not be a true maximum, but it's sort of very close to that. But yeah, it's the maximum modulus achieved by that difference on that region. So if that is very small, what that means is that the two functions are close together, not just at one point, but in fact on the entire region. You see, if the k-norm of that difference is, let's say, less than, I don't know, let's say that this k-norm is less than 1/1000th. Okay? So what that means is that if I plug in any point whatsoever into this function, and I plug the same point into the other, the modulus of that difference will be at most the maximum modulus of that difference. So that is also less than 1/1000th. And that's true for every single z simultaneously. So you see, it's not just that you're getting a convergence at each individual point z in k. It's that the convergence is happening at the exact same rate at all the points of k. Right? Because at any individual point z in k, you have this quantity which depends on z, but that is upper bounded by this quantity here, which does not depend on z. Z does not explicitly occur. And it's that upper bound that's going to 0. And that upper bound is an upper bound not just for the difference at z, but it's also an upper bound for the difference at w, or whatever, any point at all in k. So all the points in k simultaneously have the property that this difference, this modulus of the difference, are upper bounded by a single universal quantity that is going to 0. So it's pushing all of those differences to 0. Right? It's pushing this difference to 0 at z, but it's also pushing this difference to 0 at some other point w in k. And the same is true for any old point in k. All right, they're all being pushed to 0 simultaneously by the same upper bound that is itself going to 0. So that's the notion of uniform convergence. And it's clear from my description that uniform convergence implies pointwise convergence. All right, well then the conclusion of the lemma is that the limit function f of this sequence, the original sequence, must actually be analytic, at least on the interior of k. We can't guarantee that it's going to hold true on any region bigger than k. To be analytic on k itself, including at the boundary points, would mean being analytic on like a larger region, some larger region that contains k. Now we can't guarantee that, but we can guarantee that f is at least analytic in the interior of k, which is itself an open set. Right? And in fact, that other limit function g is just exactly the derivative of f. So f is differentiable, is analytic, and its derivative happens to be g, at least in the interior of that compact set k, which is open. All right, so that's the lemma. Now we have to do the proof. All right, so the first step in the proof is just showing that g has to be continuous on the set k. Notice we did not assume that, but we did assume that the functions approaching z are continuous. The functions that are approaching z are the fn primes. They're approaching g uniformly on k. And these are known to be continuous, all of them, every single one, for each n. Continuous on k, that is. I should probably say that. All right, for each n. Now, did we assume that? Well, no, because we didn't need to, since in complex analysis it follows for free. But remember this note that I made here, that in real analysis you do have to explicitly assume that. You have to explicitly make it an assumption that the fn primes are continuous on k. All right, so yeah, we're going to, one way or another, we know this. All the Fn primes are continuous on K. Now you see that G is not known to be continuous on K, but it turns out it must be. This is a remarkable fact about uniform convergence. Basically says that if a function is the uniform limit of continuous functions, then it itself must be continuous. It's a remarkable fact, right? And here's how we can prove it. So let's take 2 points in K, Z and W, and we're going to study this difference, the modulus of G of Z minus G of W. Okay. Now we can insert into there like an Fn prime of Z and a minus Fn prime of Z. Also Fn prime of W and minus Fn prime of W. They just cancel out. But then using the triangle inequality, we can break up the modulus into 3 separate moduli added together. And that gives an upper bound. Okay. Now the key observation is that this and this, both of those terms, are bounded by the same bound, which is the K norm of that difference. Because you see that the K norm of that difference is just the supremum of this expression. It's like G of something. Let me just call this something U temporarily. And then F sub n prime of that same U. But U is allowed to vary freely through K. Right? Now this expression here is of that type. It's just that the U happens to equal Z, which is one special value in K. And then this over here is also of that exact same type. It's just that the U is equal to W, which is also some special value in K. But the value of that expression at a particular point in K is at most the supremum of that same expression over all K. So yeah, those are both upper bounded by, right? It's less than or equal by that K norm. The middle term here I didn't touch. I just left it alone. It appears here. All right, so we have two of these, so we get this, and then we just have that middle term. And now the argument goes like this. Let's fix some positive epsilon, arbitrary, and we can then find some capital N where if a subscript is beyond that capital N, right, if I have a little n that's like beyond that, then we will get this inequality here. Right? And I know that that's possible to find this capital N, which by the way depends on epsilon. This capital N is going to be some function of epsilon. Yeah, I know that that's possible to find because we have assumed that the K norm of this difference goes to 0 with n, as n goes to infinity. So basically what that means is that by taking n large enough beyond some cutoff point, capital N, I can make this K norm as small as I please. And I want to make it less than epsilon over 4. See, I have this extra factor of 2 here. But by making that K norm come out less than epsilon over 4, then I can multiply by 2 on both sides, and I get this inequality. Right? Now, we can also just be a little more specific. Instead of having little n be arbitrary number bigger than capital N, or greater than or equal to, I can just take little n to be capital N, because that does satisfy this inequality. Right? And then the thing we got here, where we started with this expression, and we ultimately saw that it was less than or equal to this expression. Okay, well, this piece of it is now less than epsilon over 2. So we get this. And notice that what was a little n is now a big N, because we made that choice. The reason for making that choice is because big N is like a specific positive integer. Little n was a variable. Little n was some variable that could take on any value greater than or equal to that capital N. But that capital N is of some specific positive integer which depends on epsilon. And I need something specific, because I plan to use the continuity of this specific function. So I don't want the n to vary. I want the n to stay fixed. Okay. Now, did I need to take this particular n? No, I could have taken like big N plus 1, would have worked fine, or big N plus 2, but we just make the simplest choice we can. All right. Now, with that subscript being now some fixed specific positive integer, this function here is known to be continuous on k, which means that given epsilon, I can find a corresponding delta, positive delta, such that if I fix a z, so the delta therefore depends on z as well as epsilon. This delta is going to depend not just on epsilon, but also on z, because it's continuity at the point z. That's what I'm saying, is like fn prime is continuous on k, and z is in k. So therefore, fn prime is continuous at the point z, specifically at the point z. So I'm fixing a z, and the delta that I get, which is positive, may depend on that z, as well as epsilon. All right. But the point of that delta is that if you take a w within that distance of z, then you're going to make this difference sort of as small as you please. Fn prime is continuous at z, so its value at w is going to be very close to its value at z, as long as w and z themselves are sufficiently close. Okay, so let me say that one more time. It's a little confusing. But basically, we know that this specific function is continuous at z. Now, what that means is that if I take w very close to z, then the value of this function at w will be very close to its value at z. And I can get them to be as close as I please. And I want them to be within epsilon over 2 of each other. Since that's positive, I can do that. I can do that by taking w and z close enough together within some delta. And this delta is generally dependent on the epsilon, of course, but it's also dependent on z, which is the point at which this thing is continuous.